Hello, this is Byeonggeun. I'm going to present our work, Domain Generalization on Efficient Acoustic Scene Classification using Residual Normalization. Our work targets the task DCASE 2021 challenge, task 1A, which is low complexity acoustic scene classification task with multiple devices. Acoustic scene classification is the task of classifying sound scenes such as airport, train station, and urban park to which user belongs. This year, this task becomes more challenging as an ASC model needs to solve two problems simultaneously. One, data is collected from multiple devices, and the number of samples per device is unbalanced. Second, task 1A restricts the model size. Here are our contributions. First, we introduce a network architecture for ASC and achieve higher accuracy with efficient design. Second, we propose a novel normalization method, residual normalization, we called it Resnum, which can leverage the generalization performance for unseen devices. Finally, we describe model compression combined with pruning and quantization to satisfy the model complexity of the task while maintaining performance using knowledge distillation. As a result, we could get the first place in task 1A of DCASE 2021. Here are our approach. Our network architecture is based on BC ResNet, which is Broadcasting Residual Network, which targets human voice for efficient keyword spotting. On the other hand, we aim to classify audio scenes. So to adapt to the differences in input domains, we make two modifications. First, we limit the receptive field size, and second, we use max pull instead of dilation. So the resulting modified BC ResNet ASC consists of 9 sequential BC Res blocks. Compared to the vanilla BC ResNet 8, our modification can achieve 1% additional gain, and also it is much more than 2% better than other baselines like CPU ResNet with only a 1/3 of number of parameters. And our second approach is residual normalization. Our motivation is that we observe that differences between audio devices are labeled along frequency dimension rather than channel dimension. For example, in here, we plot a 2D TSNE visualization of vision maps of BC ResNet ASC right after the stage 2. The top one use concatenation of frequency-wise mean and standard deviation, and the bottom one use concatenation of channel-wise statistics. And as you can see, the training samples are separated better by device ID with frequency-wise statistics. Instance normalization has been a representative approach to eliminate instance-specific domain discrepancy. So here we use instance normalization by frequency instead of IN, based on this motivation here. So the resulting frequency IN is we extract the frequency-wise averaging from the feature, then divided by frequency-wise standard deviation. So frequency-wise mean and the frequency-wise variance, they are calculated over a channel and temporal axis. Frequency IN is a task agnostic and can result to loss of useful information for classification. So to compensate for information loss, we add an identity shortcut multiplied by a hyperparameter. We fix the hyperparameter lambda to 0.1 in this work. And the resulting resonum looks like this. And we use resonum at input and after at the end of every stage. So in total, we use 5 resonum model in each network. Here are some quantitative results. There are 9 devices, 6 are seen during the training, A to S3, they are seen during the training, and S4 to S6, they are unseen during the training, only for the test. So here, as you can see, the baseline shows a poor generalization capability. It shows much worse top-on test accuracy for unseen compared to that of seen devices. And after apply our residual resonum, we can get about a 7% of improvements in overall top-on test accuracy, and show a clear margin compared to other baselines. And it shows about more than a 10% improvements for unseen devices, and shows a good generalization capability compared to the others. And it also shows good results for seen devices too. This tendency also keep for the larger network, which is resonate 8. So compared to the baseline here, 69.5, we can get about a 75% top-end test accuracy with a good generalization capability here too. And we do some ablations here. If we do not use this shortcut here, it still shows a good generalization capability, but it shows a performance drop for seen devices, which means that this frequency IN itself can cause a loss of useful information, and this identity shortcut can compensate that information loss. And also this one without resonum in network implies that we use less non-ordinate input, and it shows a better results for a small network, but we observed that for a larger network, it is beneficial to use less non-ordinate input, but also in the middle of the network. Using this Resonum and the BC Resonant ASC8, we do modal compression to fit the restrictions in model size. We use a magnitude-based one-shot unstructured pruning, and we quantize all convolution radius as an 8-bit while utilize half precision for the others. And we also use knowledge distillation to compensate the performance drop due to compression. So the vanilla model shows a 76.3% top-end test accuracy. It is better than the number here because we train it for a longer time. We train it for a longer epochs, and also we use a knowledge distillation for this vanilla model. And after that, we use pruning and quantization and it results to 1% to 1.2% performance drop. And here we use knowledge distillation again, and we can slightly get better model. So this is the end of the presentation. Thank you for listening. You can find more details in our paper. Thank you.